we now have a YouTube channel with the previous talks. This will be announced with the next message for next week's talk, and Olivier's talk would be there probably by then. And well, now we can start. And then okay, the second comment. Maybe we have a new name for the. Okay, so we're happy to have Olivier Ramaré from Marseille, who speak on some additive questions in multiplicative number theory.
Great. Happy New Year to you. And I'm very sad not to be in Brazil. It's much warmer than here, and it would be more fun. But anyway, I'm in my office. Okay, some additive questions. So some background first. Yes, too many things on this slide. Since it's some additive problems, and the pretext is some multiplicative number theoretic problem. So first, I'm going to present you the problem in multiplicative number theory, and then I'll tell you that it reduces to a problem in additive number theory. So first multiplicative, and then there'll be a change of background, and we'll go to additive number theory. So in multiplicative number theory, we are looking at z by qz, and we want to find a product of 3 primes congruent to a given residue class modulo q. And of course, you want to find them as small as possible, and smaller than some power of q, and this power of q should be as small as you can. I thought it would be very difficult to do, and then finally with Aled Walker in 2016, we found a very simple way of achieving that. So once we had this very simple way of doing, we started working, so with Oriol Serra and Priambad Srivastava, to get the exponent smaller and smaller. So with Oriol and Priambad, we went to q to the cube. And you see it's still completely explicit because the method is simple, really simple. Not simple as simple group, but simple. Just to put people on the same page, if you ask only for 1 prime and not a product of 3, we know that there exists a constant so that there is a prime congruent to a modulo q and p less than q to some L, that's the constant. And that's a very difficult proof, whether you follow the work of Linnik or some more modern proof. The best exponent we have till now is most probably 5, maybe 5.18, and it's definitely not explicit. I mean, if it is explicit, it is not with decent constant. It has been a long problem to bring this constant down. One of the difficulty in particular is to control, I mean, you want P1, P2, P3, exactly 3 primes, or exactly 2 primes, or exactly 1 primes, not a prime or a product of 2, or not a prime or a product of 2 or 3. Yes, exactly 3. So because of the parity problem and something like that. Anyway, you see that for Linux constant, we have now p less than q to the 5 asymptotically. And in this theorem, you can have p1, p2, p3 less than q to the 3. The product is still less than q to the 9, but if each of them is a small. Okay, so once we had that, we continued working with Balu Subramanian. And because the previous proof was stuck at q3, I mean the exponent 3, and we wanted to see whether we could beat this 3, and that we were just publishing, I mean finishing the paper, and it will be submitted tomorrow or the day after. So we can go till 5.5. It's still explicit, but the proof is getting more complicated. So you see the constants are less good, q larger than 10 to the 30. You have the 15,000 in between. I mean, this proof can be trimmed and the constant can be lowered a bit, but to get really decent one is more work. And 5½ is still larger than 2, sorry. It's less than 3, but still larger than 2. And we wanted to see whether we could go beyond this q square. And in fact, yes. And you take the same proof we have, you forget the explicit aspect and you use the best exponent you can find. And in fact, this same proof gives you P1, P2, P3 less than Q to the 3½ plus epsilon. I mean, now it's not explicit anymore. And and this time, if you take the product P1, P2, P3 is less than Q to the 9½ which is less than 5. Yes. It's but what we really wanted to go is beyond the Q square, because under the Riemann hypothesis, Linux constant is, we know that it is less than 2. We believe that it is 1, and can believe it is 1, but under the Riemann hypothesis, we had the barrier 2, and now we have 3½ which is below. In fact, if you use the recent work of Petrov and Yang, when Q is cube 3, you can even reduce this 3½ to 4/3. You can, if you had some special condition, you can even go to a smaller exponent. We don't have 1 plus epsilon yet, but we have a rather small exponent. So I write difficulties with the large subgroup problem, which I'll just after that. Wait, I forgot something. Oh, okay. Sorry. Okay. Sorry, I changed 3 slides. So what we are going to do is that we are going to show, by using a Brontitch theorem or something like that, that the primes cannot accumulate in a given residue class. And so we are going to show that the number of classes that are reached by some primes, modulo Q, is rather large. So this is the set A. And we want to show that A times A times A covers the full group. That's when you write things with a multiplicative notation. Usually when you do some additive combinatoric, you use addition instead of multiplication. So I've written Kinesthetic Theorem, which I use here with additive notation. So you have your set A, you want to look at A plus A, which is A times A in the case of primes. And you want this set to be of a larger density, I mean, to have more elements. What happens if you look at the integers? The simplest case, if you take the element between 1 and n, take all the elements 1 to n, and you look at A plus A, you get all the elements from 2 to 2n. So you've doubled the size of the set. And in fact, in Z, if you use a finite set and you look at A plus A, well, A plus A has a size at least twice the size of the initial set minus 1, because of 0 element. There's one case. The difficulty with that is that if you are in a group which has subgroup, and your set A is already a subgroup, well, A plus A is the same subgroup. So you do not increase the size of this set. And so these are the two extreme cases. The first extreme case is 2A, A plus A is of size 2A minus 1. That's the case when you're like in Z. Or if A is a subgroup, 2A is exactly equal to A. Kinesthetic theorem is a result of the 50s, I think, that tells you how to go from one case to the other. So look at A plus A is a union of cosets modulo some subgroup. Maybe this subgroup is a trivial subgroup. Yes, usually it is. And according to this subgroup, you can compute and see what happens. So this is what you get. Essentially, what happens is that if this subgroup H is a small, you in the case 2a larger than 2a minus 1. If this subgroup H is huge, you cannot say anything. I mean, you don't increase the size. That's what I call the large subgroup problem. And it means for us, we have to show that the primes do not concentrate in some subgroup or in some given coset of some subgroup. So let's see the kind of information we have. So sorry, I have to go backwards. The first information we have about primes in subgroups, take a subgroup H of Z by QZ star, the multiplicative group, yes, and assume G by H is small. So the index is Y is equal to 2 or 3 or 5. And then it is not so difficult to prove that H contains a prime less than Q to the Y minus 1 by 3. And in fact, if you assume that Q is cube free, you can write 1 minus 1 by 4. So if H is a quadratic subgroup, I mean G by H is 2, that's good. It's Q to the 1/3. If H is, if Y is 5, a subgroup of index 5, well, you're already at Q to the 4/3, which is getting a bit large. And the next one we're going to be interested in is Y equal to 8. And you see that for 8, you get an exponent 7/3, which is larger than 2. That's a very strange problem. You want to find a prime in something which should not be difficult, a subgroup of index 8 in Z by QZ star. Yes. There's lots of elements in this subgroup. I don't know how to prove that there's such a prime below Q, even below Q square, I don't know. So we've proved that with Priambad and Balou. In fact, we just take the proof of Elliott of 71 to prove something similar. And Elliott had the condition that Q is prime, but if you work a bit carefully, you get this one by following the same proof. Okay, see, this one is...
I don't understand. Why is it Y minus 1? I mean, just with Linux theorem, you can do better if Y is 10 or 20.
Sorry?
Maybe I'm misunderstanding this theorem, but surely you have a prime in a given arithmetic progression less than Q to the 6.
Yes.
So
yes.
Once Y is bigger than 20, this theorem is irrelevant.
Absolutely.
Okay, so you just...
I'm interested in Y equal 5, 8, 11. Yes, small Y.
Okay.
Yes.
Thank you.
But it's amazing that the best you could do is to find a prime in every arithmetic progression, while you just want one in a very large set, and you don't get anything better.
Well, there's always this issue that Siegel zeros do this to you.
But well, once you have index 3 or 5, you shouldn't have a Siegel zero problem. Anyway, okay. If you don't use analytic method, there's some marvelous work of Nagel in 52. I love this result. If you write, okay, it's only for Q when Q is prime, write 4Q equal A squared plus 27B squared. And the theorem of Nagel tells you that every divisor of A or of B is a cubic residue. It's amazing. So it tells you that the smallest cubic residue is less than twice the square root of Q plus 36 or something like that. Sun worked out some formulas like that for big quadratic residues, and Medley and Pollack continued this work for big quadratic residues, so y equal to 4. And I don't have anything for y equal to 5, which is of great interest for me, or 8. But it's very interesting that the algebraic way is much more efficient, and the analytic way is way of. Okay, I just want to tell you that there are some other subgroups that we're interested in, not only Z by Q, Z star, but the Ray class group HQ of K. Take a number field K, take the Ray class group or the Laro Ray class group if you prefer. I mean, any quotient. And you want to find a prime, so prime ideals of degree 1, of course. You want them so that the norm should be small in terms of the norm of Q. Yes. So now we have 16 by 3, but it's being improved in between. And you want each class of this class group to contain a product P1, P2, P3. I'm telling you that because it means that the group that we're looking at, it's still a finite abelian group, but it's different. Yes. And sorry. And of course, if you want a single prime ideal, you have the work of Zaman, which gives you some exponent like 40 or something like that. Okay, time. Let me see. Okay, good. Now let's see to. Okay. When we use Kinesthetic Theorem, I want to show you some things that happens. So you see in Kinesthetic Theorem, you have your set A, which is a set of classes of primes, yes, and you want A plus A to be large, and you have H, which is the subgroup which is stabilizer of A plus A, or A times A if you write multiplicatively. And so what happens? First, you have to see that 2A is a union of H cosets, yes, and 3A is also a union of H cosets, though A is not a union of H cosets. It means that you can go and work in G by H, in fact. Just take A star to be A by H, and now you can work in G star, which is G by H. And because 2A is already a union of H coset and 3A also, it's enough to show that 3A star is exactly equal to G star. Yes? That's really what you have to do. So now we are working in a very small group, G star, which is of cardinality 5 or 8 or something like that. Yes? And if you work some, I would say algebraic nonsense. I mean, work with all your quantities, see your density and so on, and you discover that you have a problem only if the index y is congruent to 2 modulo 3. So y equal to 2 is a difficulty, y equal to 5 is a difficulty, y equal to 8 is a difficulty, and 11. That's why I'm always quoting 5 and 8 that are my main problem. And the Brontitch March stuff is going to tell you that the density of A is larger than the density of the group divided by 3 or something more. And you want to show that 3 times A or 3 times A star is equal to G star. Yes? So please recall that if Y, the index, is large enough, you're done. And if the index is not congruent to 2 modulo 3, you're done also. So we only have the problem with some special cosets. So here's the basic problem that I'm writing. I write G instead of G star. Take a finite abelian group. Is a subset so that A by G is larger than eta, which is larger than 1/3. And if you were in Z, it would be enough to ensure that 3 times A is G. And you want to find conditions so that 3A equal to G. And so what are the conditions you have? C with the primes, you can say that every element of your group is a product of primes. Yes. So you can have as a condition that A generates G. Okay. So it's the complete set. But it can still be contained in a single coset of something. But it generates everything. And you can assume that A intersects every subgroup of index 2. That you can do with a potency. And so these conditions, you can easily verify them, so by Brontitch March inequality or variance of it, and by what I showed you about primes in a subgroup. Yes. Okay, so the first result we have, which is the trivial one, if A by G is larger than 2/5, then 3A is equal to G. Why is it like that? Because we avoid the index y equal to 5. We only have the index y equal to 2 to worry about. But we know that there is a prime in a quadratic subgroup and there is a prime out of this quadratic subgroup. So we don't have any problem with the index y equal to 2. And the index y equal to 5 is ruled out by this condition. But now, if you have the set A star, which is equal to 0, 1, which is of cardinality 2, so the density is 2 by 5, yes, 3A star is not equal to G star, because it's 0, 1, 4, and 0, 1, 3, and 4 is missing. So we have to rule out this case. Okay, that was where we were, and so we wanted to do something better. And here is what we can do better. If you think of the Brontitch March inequality, it tells you that the number of primes in a given class modulo Q is less than twice what it should be. Essentially, not maybe 2, maybe a bit more, maybe 2.5 or almost 3. Okay. But usually we believe that this factor 2 is here because we don't count only primes, but we count also product of 2 primes. So if you take the same ID and you use the weighted sieve instead, you can prove, in fact, that every class modulo large subgroup contains either a prime, either a product of 2 primes. It's another way of looking at the Brontitch March inequality, but it gives you an additional condition. The additional condition is that, so finally, your set of primes or product of 2 of them covers every class, covers every coset modulo large subgroup. That's the condition that I've written here. You have A union 2A, which intersects every coset. That's an additional condition that you can have. And in fact, that's the main news of this talk, if you call that news. That's very surprising because from a sieve viewpoint, you have the feeling that you don't do anything more than the Brontitch March inequality. You really have the feeling that it's the same thing. But you get a way different information out of it. I don't exactly understand why it is like that. So just now for Ray class group, I'm not sure I'll be able to do it, but my guess is that we will do it. So for instance, if you go back and my example 0, 1, 0, 1 is not a counterexample anymore because 2A star, A star union 2A star is not G star. So I can rule out this example and I have to see what I can do more than that. I was in Chennai with Balu and Priyamba. It was at the time when we could travel. We would go to India. We would have coffee and tea, and we could work in the morning and then decide that it was too difficult and go for tea. I mean, things like that. Now we are home and we work more or less. I don't know. So yes, so that's the result I'm quoting. The fact that why we can have this condition in the additive setting is that every coset UH, so multiplicatively, contains a prime or a P1, P2, with P1, P2 less than Q. In fact, you can, provided Q is larger than Q naught of Y and Y in the index, yes? In fact, you can find P1, P2 even smaller than that. Brown has done that for every single class, but the exponent was 2 minus a bit of something. I mean, he had beaten the exponent Q square, the level of Q, of course. Okay, that's essentially what happened is that because your subgroup is large, the error term you have doesn't have any dependence in Q. If you look at a single class, your error term is multiplied by Q, and if you look at the large subgroup, your error term is not multiplied by Q, and that's why you save a lot in your error term. And so the weighted sieve gives everything without any difficulty. So that's something interesting in the way you work. When you work for a single class, you parameterize this class. You know, it's A plus MQ, and then you work on M, and you have your sieve work on M. Yes. So it is the set of M that you sieve in some way. In this setting, you look at your integer n that you want to be a P1, P2, and you recognize the fact that it belongs to this subgroup by using characters. But you use only a finite number of characters, I mean, only Y characters. So your error term is only multiplied by Y. It's very different. It's a very different process. Here you recognize the primes, and for the other Brontitch march, you parameterize the progression. Anyway, so now we need a general lemma to see what happens. So you have G star, your finite abelian group. You have a set A. You assume that A star union 2A star is equal to your group. And you would like 3A star to be equal to G star. If you have 3A star equal to G star, you're home. Okay. So let us assume that it is not equal to G star. And you want to see what happens. What happens? The main interesting thing is the first one. 0 does not belong to A star. That's really the main thing. So it means that if you want to rule out this 3A star equal to G star, you only have to show that 0 belongs to A star, which means that you only have to show that the primes belong to a subgroup and not to a given coset. That's what we have. So till now we were able to show that at least for index 5 that there was a prime in a given subgroup, and that will be enough thanks to this condition. The situation is rather rigid, so you can say that the stabilizer of A star is 0. I mean, here we assume that the stabilizer of 2A star is trivial. There's no stabilizer. And then you discover that A star is in fact sum free. So A star union 2A star is G star, and A star has no intersection with 2A star. Once you have that, it's easy to show that A star is small. and that in fact 3A star misses only the class 0. I don't exactly understand where all of that is coming from. So that's what happens. Some free sets in finite abelian groups have been classified by Yap in 75, Hong Kong or Thailand, I don't remember, and by Green and Imre Rouja in 2005. I mean, they completed the classification, but it doesn't. I mean, it's not exactly the same classification as the one that we would like here, because here we have more conditions. They've classified the sum free sets, and they found the larger possible cardinality. In this case, we have some more conditions. So the classification is not exactly the same, though I tend to believe that it will give the same result, but I'm not exactly able to redo the work of Yap and Green and Rouja to find that. I'm going to give you a
Olivier, this is very much like Kemperman's theorem when you're doing Z mod QZ. So Kemperman's theorem classifies all the A plus B's that just miss being Z mod QZ when the size of A plus the size of B is Q minus 1. Or is Q rather. Yeah, so that's exactly your situation.
Okay, Kemperman is when Q is prime, no?
Yeah, no, I don't think Q's, maybe it is, but Phyllis, this is the same result.
Okay.
I mean, it's saying more or less the same thing as Kemperman's theorem, which is, I mean, the main thing, part 3, as you point out, is the most surprising bit. And Kemperman says exactly that kind of thing.
Yeah, but I don't think there's a condition that A star union 2 A star is G.
No, but that means the size of A star plus the size of 2A star is equal to the size of G. So that is exactly the condition in Kemperman's theorem.
Ah, okay, yes. Good. So I have some work to do after this talk. I have to give you a
of some sort, but it does fall in that tradition.
Well, I'll check Kemperman's theorem. So, because it's very easy, so I could give it. I mean, usually I would tell you, when you go home, you'll take a plane and you'll have time to prove this theorem. But since we're not in usual time, you won't take a plane, so I'm going to give a proof. Because this proof is very easy and I cannot miss it. I mean, I hope I cannot miss it. So just look at G star minus 3A star, and you assume that it's non-empty. And you discover, if you think of it, that it's a set of G, so the G minus really not, minus A star, has no intersection with 2A star. Once you find that, if G is in gamma, you find that G minus A star is included in A star, because it cannot be in the other part. And so G minus A star is equal to A star. And of course, if it was G plus, you would be home, you would say G equal to 0, and I mean, you would say, yes, G equal to 0, because A star has no stabilizer. A stabilizer of A star would stabilize A star plus A star. But you have a minus, so you have to play some game. So to get rid of your minus, you do it twice. So because minus get you plus, so you discover that G1 minus G2, if you have 2 elements in gamma, it will stabilize A star, so it is 0. I mean, if it stabilizes A star, it stabilizes 2A star, and so it is 0. So you discover that there's only one element in your set. And then then you're not happy, you'd like this element to be 0, and you push your equations in whichever way you want. Maybe there's a simple way of seeing that, but I've only been able I mean, with Baloo, we've only been able to push things in this manner. Finally, you discover that the only element possible is 0. So you see, if you look at this set gamma, the proof is really essentially straightforward. But it's pleasant to have an easy proof that gives a good result. Okay, that's almost the end of this talk. I'm going to give you some consequences. So since we are able to show that there is a prime in a subgroup of index 5, we can go beyond this index 5 and go till 3 by 8. So if A by G is larger than 3 by 8, we have 3A equal to G. That's what we're able to do now. Of course, the aim is to go as close to 1/3 as possible. Okay. So this one is 0.375. And so we try to go a bit beyond this one. So next, I told you that the indices that are difficult are the ones that are congruent to 2 modulo 3. So the next one is 8. 5 was the difficulty. The next one is 8. Then the one after that is 11. So if you want to go on the other side of 8, just look at all the examples, or all the sets you have in a subgroup of in an abelian group of cardinality 8. You have 3 such subgroup, z by 8z, z by 2z times z by 4z, or z by 2z cube. It turns out that if the 2 part is isomorphic to z by 2z to some power, so you don't have any z by 4z or z by 8z, then we can rule out the factor 8. And we can go till 4 by 11, getting smaller. We have some conditions on Q for which this will work. So why is it? So I told you that G star can be only one of these 3 groups, yes? And because of our condition, the only one we can have is z by 2z cube. But A star is going to be a basis of G star, which happens to be a vector space. But because it is a basis, there's an element which is the sum of 3 elements of A star and not of 2. So it's not possible because we've assumed that A star plus 2A star is equal to G star. So this case doesn't happen, and A star is bigger, and we are happy. So what I like with this result is that by using the structure, by looking really at what happens, you can rule out a case. That's why we decided to publish it. Okay, if you want to look at what happens in general, so if you look at z by 8z, the 2 examples we have is 1, 4, 7 and 3, 4, 5 that you have to rule out. But when I tell you 1, 4, 7 or 3, 4, 5, you have to see that it is in additive notation. So it means that if you go back to primes, there should not be in classes that are congruent to u times h, or u to the 4 times h, or u to the 7 times h on the other one. And I don't really know how to rule this kind of thing out. Algebraic number theory is really to be used. That's pretty clear. But I've not been able to understand really in terms of ideals what it means and how I can. So the case z by 2z times z by 4z, I thought was a bit more welcoming. You have only 4 possible sets for A star. You can rule out 2 of them, the second and the fourth. So you have only 2 cases that are possible. And once again, if I'm pretty sure that we should use algebraic number theory. By using algebraic number theory, we could work out more. We could get more on this situation. But just now I'm essentially stuck. So I just wanted to show you that. So some more information about the bound. You see in this theorem, I told you that A star is less than G star plus 1 divided by 3. And then with Baloo, we thought that the situation was completely rigid, and we thought A star was essentially equal to G star plus 1 by 3. So if it's a sum-free set and we have this condition, it should be essentially equal to that. And it's false. I mean, now we tend to believe it is false. So there's an example by Desouillet and Lev, I think. If you take this group Z by 3k plus 2Z and you take the middle interval k plus 1 to k plus 1, so it gives you a set that verifies your condition, and that's cardinality exactly equal to G star plus 1 by 3. So we know that this upper bound is optimal by this example. But again, I don't know how to rule out this example in terms of primes. And then we started running some numerical experiment in only the case Z by LZ, because it was getting too complicated. And it turns out that we found sets A that were of lesser cardinality than G star plus 1 by 3. We found for modulo 29, we found a set of cardinality 8, which is rather small, and the larger L, the smaller the set. If you want to continue, I can give you some specific example that we are trying to rule out. And for instance, if you want to work modulo 48 or 49, we have a very small cardinality example by using a set that has C union minus C. Essentially, we tend to believe that that will be the smaller examples that we can find that have only this number of elements. So this one has 8 of them, so it has only 16 elements, and we would believe that there should be more. At the beginning, we thought there should be more. So finally, maybe A star can be real small, and A star union 2 A star be rather large. Essentially, we don't understand the structure of these examples, and we don't understand how to use algebraic number theory to rule that out. So that's also why I was giving this talk to not exactly to send the problem to some other people, but if some other idea comes in, I would be happy. And that's the end. So I'll go back to this one. So what is open essentially is to get smaller exponent here, closer to 1/3, and to get conditions that you can verify in terms of primes. And I'm sorry I'm finished too early, but I told you it was a small, little talk or small talk. I don't know what I should say. Thank you.
Thank you. Well, are there any questions?
Can you indicate what the weighted sieve looks like in this case where you identified the arithmetic progressions of a subgroup or cosets of a subgroup?
Mm-hmm. What? Yes.
So how do you construct the weights here to work well with a subgroup or a coset? What do they look like?
You just use standard work of grids. I mean, the only thing is that the distribution level is larger than what you expect, because you don't multiply by Q, in fact. I mean, you know, the weight are just the grids weight, or I mean, essentially in this case, you could take the usual, I mean, 1 minus the sum of the small primes dividing your guy times the Selbach sieve. I guess it would work. The thing is that you save in the distribution level because you don't multiply by q. To recognize that an integer is in this subgroup, it's 1 upon y times the sum for chi in g by h, I mean, the dual of g by h, of chi bar u times chi of n. So you have a sum upon only y characters. And this means that in your error term, you have a q less. Instead of multiplying by q, you multiply by y. We essentially take something which is straight out of the box. We don't do anything special, but the distribution level is.
So, okay, so the level of distribution that you get using these arithmetic progressions somehow beats what you get with an individual one.
Yes.
So what is the trick for that? You know?
It's only because the sum upon your characters has only a finite number of characters. You don't have q of them. Usually you have q characters. Here you have only a finite number of them.
Okay. I mean, some of this, there's a win that takes place.
Yes.
Technically, but I'm not seeing where it is.
So is it like an example of this is like you counting primes which are, I don't know, square modulo something instead of something like this?
Yeah.
So
yeah, you can work out a Brontitch march inequality for we've done that with preambed. If you count the number of primes that are congruent to a square with a prime, in a quadratic subgroup, you can go beyond q. I mean, you can take an interval which is smaller than q. The fact that you have only a finite number of characters and not q of them is where you get your win.
Okay.
Essentially, you lose for the Brontitch mass, you lose the Gauss sum, so you lose the square root of q instead of losing q. And here you get the same the same thing. So the dependence in y is rather wild. If you have y equal to q or phi of q, you get a very bad result. If you take y equal very large, you really lose more than if you look at individual arithmetic progression. So it's not smooth transition between subgroup to one individual class. There's a transition around square root of q.
So I guess the character sums are giving you the level of distribution, so you get a win down to about q to the quarter or something.
Yes. But it's really that you have only a finite number of characters to worry. It's that's where you get. That's.
So can you? There's a small integer that's a product of less than or equal to 3 primes. Can you get a better result for that problem? Here you're working with exactly 3 primes, right?
Yes, Jean-Marc was telling me this question, was asking me this question, and I think that in fact I cannot do better. Because if you look at the, I mean, That's strange. I was thinking about if you look at the result of his Brown, so 78, he proves that every congruence class modulo Q contains a P2 number, so less than 2 prime factors, and but each of them is less than Q to the 2, well, 1.8 or 1.9, something like that. And here we can get 3/2. And so I cannot get a small exponent if I use only 2 primes. We cannot, if I'm not mistaken. But maybe if we can prove that the P1 or P1 P2 is both of them less than Q to the 3/2 is congruent to A mod Q, which I'm not. I have to compare, but the fact is that I don't remember whether the result of his Brown is that you have a P1 P2 less than Q to the 2 minus something, or whether it's P1 P2, each of them being less than Q to the 2 minus something. That I don't remember. I think it's P1 P2, the product of them being less than Q to something.
But if you just use a standard analytic number theory, the P1s plus P2s with the usual weights, then you get less contribution from the zeros near to the 1 line. I mean, that's why you get the elementary proof of the prime number theorem, for instance. So you might hope to do substantially better.
Yes.
I don't know if somebody's tried to work through.
No,
essentially, you do zeta prime prime over zeta if you do that. Integrating.
Sorry, I didn't get the last sentence.
Well, instead of doing zeta prime over zeta, when you're integrating,
Yes.
which gives you a double pole at s equals 1, and that dominates better.
Yes, yes. But concerning the dependence in Q, it's not so. I mean, you have to see what you get. So, but really, I think that I do not get anything better if instead of having 3 primes exactly, I get 1, 2, or 3 primes. This is strange, but it doesn't seem to be made for that. Jean-Marc asked me this question one month ago, and no, that's also strange if you look at this argument with P1 or P1 P2, because in the argument we are going to use them as if they were in the same set. I use A star union to A star, but in fact, if they are P1, they are large. They are close to Q to the 3/2. But if they are P1 P2, each of them is very small, because P1 P2 is larger than P to the 1/2, let's say. So each of them is less than Q to the, I mean, your exponent minus that. So in fact, this set A star union to A star, I'm treating them as if they were coming from the same bin, but they are not. Anyway, it works. But it's maybe we could treat them differently. I still have not haven't decided about that. There's something strange in this way of using Brontitch marching. I mean, the fact that we are losing a factor 2 in Brontitch march in two different ways. Weighted sieve in one part and the factor 2 in the other part. I mean, density and covering. I'm still not really sure how to explain properly this phenomenon. The fact that they don't come from the same bean is something to do with it. That's all.
Okay.
I like this view.
Any other questions? Okay, not a very important question, but you mentioned that you used Young and Petro's result.
Yes.
But so what exactly do you use from them? The estimate on character sums?
No. L prime less than Q to the 1/3.
Okay.
Because for this theorem here, let me think for this theorem or for another one. Wait. No. It's for another part. We have an almost everywhere Brontitch inequality, where we use the L infinite norms of LS chi.
Okay.
And if you use Young and Petrov, you get a better exponent. So it's a density. It's not in this part, which is the additive part, but in the multiplicative part, we get a better exponent. So we get a better almost everywhere Brontitch inequality.
Mm-hmm.
And essentially we use their result without knowing anything that they do. The exponent is Q to the 1/3, and it gives something better. We have a proof that uses the L infinite norm of LS chi instead of the forced power moment or something like that. So as soon as you improve on the L infinite norm, you improve the almost everywhere Brontitch march, which improves the density and blah blah.
Okay.
It's really using a very powerful tool for for a smaller result, which is an almost everywhere Brontitch march inequality, but it's the best we get in this manner. I mean, dispersion method gives worse result. Many other very complicated things give worse result, and you use the L infinite norms and stuff.
I think any application of a result on L functions to deduce anything about primes is good and welcome.
Yes. No, it's true. If you give me Lindelof, I can do
Sure.
I can do marvelous things.
I mean, so every time you transform anything about L functions into something about primes, I know Fouvry is very happy about it.
Yes. But at the beginning, I saw that using the L infinite norm was a very bad idea, and I was not happy with myself at the beginning. And then I discovered that a simplistic proof using the L infinite norms instead of the force power moment and the 8 and complicated things.
I think in what
Motohashi was using the force power moment. Well, there's a beautiful proof by Mikawa that using the dispersion method for almost everywhere Brontitch march. But anyway. Just now, one of the problems that I find really puzzling is how can we find a prime in a subgroup of index 8, which is less than Q to those 3/2. Take Z by QZ, take a subgroup of index 8 of Z by QZ, and you want to find a prime in this subgroup, and you want it to be less than Q square, and I don't know how to do that. which I'm feeling bad about that. Because there's no, I don't know. We used to have difficulties with equal zeros or things like that, and here we have a large set that has some structure that we have lots of tools, and we cannot even go. I cannot go even beyond the Q square. Aled Walker has been able to prove that the primes cannot be contained in a single class.
That's reassuring.
Now we're somehow able to prove that a class times the union of two of them is covering everything. We are really in a bad position with primes in cosets of large subgroup. Maybe the algebraic way is a good way. I'm a bit surprised that we are that the results we get are so bad. I mean, okay.
Okay, that was very nice.
Thank
you again.
And I see you next week.
Definitely, yeah. Everybody's welcome next week. We have
still going to be on Thursday.
Sorry?
It's going to be on Thursday.
Also Thursday, same time, yeah. Okay. And Cathy, who's here, is gonna talk. Hello, Cathy.
Salut Olivier, tudo bom? Estamos aí.